final piece to this first section of Chapter 12 is to look at pH. And pH is a concept that you may have seen before. It's probably the most likely topic you've seen if you've ever done any acid-base chemistry. The first thing it's important to note, and this is because this is commonly confused, pH has to do with concentration. pH tells us nothing about how strong an acid or strong a base something is. And that shows in the calculations. pH is literally equal to the negative log of the concentration of the acid. And that can be expressed as H plus and is also often expressed as H3O plus. But we essentially use those interchangeably because if we're dealing with aqueous solutions, which is what we are in this class, then if we have any H plus, it reacts with water to form H3O plus. So these two terms get used pretty interchangeably. Typical pH values range from about 0 to 14, where a pH of less than 7 is considered to be an acidic solution. Greater than 7 is considered to be basic, and a pH of exactly 7 is considered to be neutral. Now, for any neutral solution, we can write this expression that we've seen before. Two water molecules react to form H3O plus hydroxide. And so we can write an equilibrium expression. Kc is equal to H3O plus times hydroxide over water squared. Just like we did with our Ka equation, we're going to pull the concentration of water out. And so we get Kc times water squared is equal to H3O plus times hydroxide. And we define this whole thing as Kw, or 1 times 10 to the minus 14. So in other words, and this shouldn't surprise us, if the concentration of H3O plus is high, then the concentration of hydroxide will be low. And if the concentration of hydroxide is high, then the concentration of the acid is low. So these two are inversely proportional to each other. So if we know any one term here, we can use it to calculate the other. And let's do that. So if in a solution the concentration of hydroxide equals 0.1 molar, what is the pH? So two separate ways that we can go about doing this problem. They're both going to get us to the same place, just putting the set of steps in a different order. So we know that Kw is equal to hydroxide times H3O plus. Kw is 1 times 10 to the minus 14. This is 0.1 molar times H3O plus. Divide both sides by 0.1. Tells us the concentration of H3O plus is 1 times 10 to the minus 13 molar. In order to find pH, we can take the negative log of that, 1 times 10 to the minus 13 molar, and that tells us that we have a pH of 13. Now, does that answer make sense? Hopefully the answer is that yes, it does make sense. Why is that? Well, let's look at, if the concentration of the base is 0.1, that's much, much larger than the concentration of the acid, which is 1 times 10 to the minus 13. So this is a solution that is mostly basic and therefore should have a basic pH. Now I said that we could have done this another way. And that's by starting by taking the negative log of both sides first. So the negative log of Kw, 1 times 10 to the minus 14, is just 14. The negative log of H3O plus, well, that's our definition of pH. And the negative log of OH minus, we could define as POH. So we could say that 14 is equal to the sum of pH and POH. In this question, all we need to do then is calculate POH. POH is the negative log of, in this case, 0.1, which is equal to 1. So 14 is equal to 1 plus pH, or pH is equal to 13. So same steps, just done in a slightly different order, but same result. So at this point, you should stop here and open up in-class exercise number 20, labeled pKa and acid and base strength, and work through those problems.